be continued for a second. Let's look at a simpler version of this. Okay, let's look at a simpler version, which is let's look at the limit as x goes to infinity of let's say 5x squared plus 2 divided by 10x squared minus, well, 6x plus 7. It doesn't even matter. Okay. Let's look at this. Let's look at this example for a second here. Okay. So what do we need? We need to figure out what happens as x goes to infinity. Okay. As x goes to infinity, notice how the top and the bottom, if you think about what happens in the lead terms in the top and the bottom, this thing begins to dominate the top, and this thing begins to dominate the bottom. Okay, so as x goes to infinity, lead terms dominate. And really what happens is this thing becomes really the same as the limit as if we were just looking at the most important powerful terms in the front. 5x squared, okay, over 10x squared, right? Which is, if you simplify this down, it equals 1/2. The limit as x goes to infinity of, if you just simplify it, 1/2, then it becomes, that's what this thing has a limit of. And if you actually graph it, and I'm gonna, this is not responding very well. Open a new one. If you graph it, you can see that this is true. So as we send x to infinity, when we're dealing with a rational function, really what we end up doing is comparing the lead term. So if I have 5x squared, what did I have? I had 5x squared, what did I write? Plus 2, and then 10x squared minus 6x plus 7. $10x squared minus 6x plus 7. Okay. Okay, that's what the function looks like. But notice that we don't necessarily, we can't necessarily tell, no, actually, if you look at it, you can tell that it's going to 1/2. So if I plot the line y equals 1/2, I plot that line, you can see that that truly is the horizontal asymptote for this function. And I'll take it and I'll turn it red so we can see it. And then if we start to zoom in on this thing, we'll see that this function basically goes towards 1/2. Okay, so the horizontal asymptote of this function really is the line y equals 1/2. Okay, it really is. So the shortcut way to do an infinite limit of a ratio is just to look at the value at the leading terms. Okay. In this case, you want to do a little more, though, in general. So what I want you to do is, to show this is that I always want you to factor out the lead terms from the numerator and the denominator. Okay, and if we do that, then we'll be able to show this a little more rigorously. So if I look at this right here, if I factor out, what's the lead term? The lead term is 5x squared. Okay, so if I factor out 5x squared, I'm going to put 5x squared out here. And then what did I have in here? I had 1 plus, and the point was to get this in the denominator, 2 over 5x squared. I see how I took it, I factored it out of the top, and now I'm going to factor this out of the bottom. So all I've done is factor. That's it. This becomes 1 minus, and I have 6x over 10x squared okay? And then I have plus 7 over 10x squared, right? And what happens inside these parentheses as x goes to infinity, right? Here's the note, okay? Is that 1 over x always goes to 0 as what happens as x goes to infinity. So if there's ever just a constant with an x in the bottom, then it's going to 0, like right here. See, this is going to go to 0 as x goes to infinity. This is going to, notice, so we have an x over an x squared. So those would cancel out and be over x. So these things are going to 0 too. This goes to 0. This goes to 0. All these things go to 0. And what this limit now is equivalent to is I can cancel, I can simplify all this stuff. You could say that this limit is now equal to, well, to 5 over 10, which is equal to 1/2. Okay, so that's the answer for this little sub-example that I did. Okay, sub-example. Did you follow the reasoning on that one?